What you are seeing is not a scene from a sci-fi movie about a journey to the center of the Earth. This is reality, taking place at a record depth of 2,300 meters beneath the eternal, snow-capped peaks of the Swiss Alps. To give you an idea of the scale, if we place the 828-meter-tall Burj Khalifa inside the mountain, it would take nearly 3 of them stacked on top of each other to reach the surface above this tunnel. Welcome to the Gotthard Base Tunnel, the longest and deepest mountain railway tunnel ever built by humanity. A project that consumed a massive budget of $12 billion for its 57-kilometer length. However, that number is still not the craziest part of this megaproject. What makes global engineers hold their breath is the terrifying heat of up to 46 degrees Celsius underground and the 1,000-ton pressure of squeezing rock, a geological condition that can crush the strongest boring machines like a soda can. How could humans operate massive tunnel boring machines the length of 4 football fields to crush 28 million tons of hard rock over 17 grueling years? Why, in a mountainous region with the most complex and treacherous geology in Europe, did we decide to punch straight through instead of choosing a safer route on the surface? And the biggest question, how could 2 giant drill heads starting from opposite sides of the mountain meet with an error of just a few centimeters after a journey of dozens of kilometers in the dark? In this video, we will decode with you how Swiss engineers conquered the rocky core of Europe to create this enduring miracle. Before we begin, don't forget to hit like and subscribe to support our upcoming videos on megaprojects. Now, let's get started right away. To understand why the Swiss accepted the risk of such an extreme project, we need to look at the geopolitical map of Europe. Switzerland is centrally located, wedged between 2 industrial powerhouses, Germany to the north and Italy to the south. For centuries, the majestic Alps acted as a natural wall, thousands of meters high, blocking any direct routes connecting these 2 giant markets. All cargo flows had to pass through Switzerland, but instead of gliding on a straight line, transport vehicles faced a miserable, climbing journey through winding mountain passes, causing chronic congestion and severe environmental pollution. That is why the Swiss government decided to punch a straight path through the base of the mountain, a pinnacle engineering technique known as a base tunnel. The goal was to turn the Alps from an obstacle into a high-speed corridor, shifting all cargo traffic to the railway. However, to achieve that flatness, engineers had to take the tunnel down to 2,300 meters below ground, the starting point of challenges far beyond the limits of human endurance. To optimize construction time for a project 57 kilometers long, engineers did not choose to dig progressively from just the 2 tunnel portals, as this method would extend the schedule by decades. Instead, they deployed a network of access tunnels and vertical shafts up to 800 meters deep, straight from the mountaintops down into the earth. At these tunnels, engineers could bring personnel and equipment deep inside to open multiple construction points simultaneously, dividing this 57-kilometer route into 5 independent sections, allowing thousands of technical staff to work in parallel at different locations beneath the Alps. First is the northern portal section at Erstfeld. Due to its proximity to residential areas, engineers had to prioritize the controlled blasting method to maximize the elimination of vibrations. The process began with robotic arms drilling dozens of small holes deep into the rock face, according to an extremely precise geometric pattern. Explosives were packed in and detonated in micro-delays, with the goal of concentrating the pressure entirely on breaking the rock at the center, avoiding the spread of shock waves that could affect civilian structures on the surface. Immediately after the dust cleared, specialized excavators moved in to clear the rubble. The technical team instantly sprayed a layer of high-pressure concrete to temporarily lock the cracks. Next, rock bolts meters long were drilled deep into the mountain, acting to link the geological layers together, keeping the tunnel roof structure absolutely stable before taking the next step. Once deep into the center at the Amsteg section, the nature of the work changed completely as engineers began to deploy the TBM, or tunnel boring machine method. However, bringing these 2,700-ton machines into the mountain was an extremely difficult logistical problem. The TBMs had to be disassembled into tens of thousands of small components, transported through access tunnels and vertical shafts to be assembled in giant caverns pre-excavated in the mountain. Here, engineers spent months manually assembling this 400-meter-long machine. Just one small mistake during assembly could cause the multi-million-dollar machine to get stuck in the middle of the Alps. When the system started, the giant cutting head equipped with dozens of ultra-hard tungsten cutters began to rotate to crush the granite layer. The process operated as a closed, automated production line. As the cutting head advanced, rock rubble fell into a hopper and was continuously carried out of the tunnel by a conveyor belt system. Right behind the drill head, hydraulic robotic arms performed the task of assembling the precast concrete segments, locking them together to form a permanent circular tunnel lining. The simultaneous coordination of drilling, clearing rock, and building the lining helped the construction team achieve a record speed, 40 meters per day. The biggest challenge appeared at the Cedron section, where the tunnel lay at a record depth of 2,300 meters. Here, engineers faced the squeezing rock phenomenon. Under the static pressure of billions of tons of mountain rock above, the rock masses no longer behaved as solid matter, but began to plastically deform and flow into the tunnel, generating a 1,000-ton pressure on the structure. Engineers had to switch the construction method to traditional drill and blast, combined with the yielding support system. They installed steel ribs equipped with special sliding joints. This system allowed the tunnel cross-section to actively shrink a few centimeters to release the accumulated geological pressure energy. Only when the pressure energy was fully released and the rock masses reached a new state of equilibrium was the permanent concrete layer sprayed on to secure the entire structure. At the Fado section, the hardest problem was the natural rock temperature reaching up to 46 degrees Celsius, turning the working environment into a giant furnace. A massive cooling system had to continuously pump thousands of cubic meters of cold water from the surface down through the vertical shafts to lower the ambient temperature to 28 degrees Celsius, ensuring survival for the workers and the operational capacity of the machinery. Because Fado also serves as a multifunction station with connecting tunnels and refuge areas featuring complex geometry, rigid TBM machines could not handle it. Therefore, engineers combined the drill and blast method to manually expand the space, creating giant caverns for future rescue and technical operations. Finally, the Bodio section, the southern portal. Here, because the geology was somewhat less stable than the granite in the center, the TBM excavation strategy was adjusted. The process of assembling the concrete lining rings was carried out with a higher density and immediately after each advanced cycle of the drill head to prevent subsidence, ensuring the tunnel was firmly shaped in weak geological conditions. As the drill heads advanced dozens of kilometers into the mountain, another logical problem arose. How could two drills starting from opposite sides of the Alps meet at a single point? At a depth of 2,300 meters, all GPS signals were completely blocked. To solve this, engineers relied on a measurement system combining laser surveying and highly sensitive gyroscopes. Coordinate landmarks were set extremely carefully from the portals, then continuously guided through each meter of drilling by a guiding laser beam. Any small deviation in the early stages would lead to hundreds of meters of misalignment upon reaching the center. On October 15, 2010, the historic moment took place. the final breakthrough between the Cedron and Fido sections. The margin of error between the two tunnel ends after a 57-kilometer journey was a mere 8 centimeters horizontally and 1 centimeter vertically. An unimaginable number proving the power of absolute precision in human engineering thought. Beyond the record for length, the core factor that sets Gotthard apart is the principle, flat tunnel. In typical mountain tunnels, trains still have to climb a certain gradient. But with Gotthard, engineers created a nearly perfectly horizontal route, with the highest point at only 550 meters above sea level. This characteristic allows super heavy freight trains up to 4,000 tons to travel through the mountain at high speed without the need for auxiliary towing locomotives, optimizing energy consumption and transport efficiency. The second difference is the design of two independent parallel single-tube tunnels. This structure optimizes the ability to disperse geostatic pressure and ensures ultimate safety. Smoke and heat from one tunnel cannot cross into the other during a fire. Another important highlight is the pressure relief door system. When trains running at 250 kilometers per hour create a highly compressed air mass, heavy steel sliding doors can open and close synchronously in just a few seconds to release the pressure, protecting passengers' eardrums and the train car structure. After 17 years of construction, with over 2,400 workers, the Gotthard Base Tunnel officially began operations, cutting travel time from Zurich to Milan to under 3 hours. More importantly, this mega-project freed the valleys from truck pollution, shifting the cargo flow to a clean and efficient railway system. This is not just a tunnel, it is a symbol of conquering nature with human intellect, perseverance, and engineering solutions ahead of their time. Thank you for joining us on the journey to decode this megaproject. If you are passionate about in-depth megaproject analysis, hit like, subscribe, and turn on the notification bell so you don't miss the next superstructures. For now, goodbye and see you in the next analysis videos.